Now that we've talked about the design and implementation of the experiment, let's talk about our findings and what we did to get them. The instrument we used to collect our data is a CD48 coincidence counting board. It's a small device that has 4 inputs consisting of 8 counters. We used inputs A and B and counted the individual counts of entangled photons from each of the avalanche photodiodes, as well as the coincidences using the first 3 counters. We connected the coincidence counter to our computer using a USB interface and used Python on Jupyter Notebook to communicate with it. In our code, after importing some important libraries and packages, we first established a serial connection with the coincidence counting board. After setting parameters for the plots, we continuously read and plotted the counts from each photodiode input and also the coincidences. Towards the end of our code, we create and write to a file to save the data points we have collected so far. As mentioned in the previous video, our code also controls the voltage on the PZT. The coincidence counter has a software-controlled DAC voltage output ranging from 0 to 4.08 volts. Our code manipulates the voltage by continuously giving a command in a loop. The coincidence counter is connected to an amplifier which allows the voltage applied to the PZT to go from 0 to 60 volts. Once the voltage reaches the maximum, the program directs it to go back to 0 in a continuous manner. This voltage is what makes the PZT expand and contract, and this process produces changes in the interference pattern. We collected data to produce a plot of coincidence counts versus time, with time being approximately proportional to PZT voltage. We observe an approximately sinusoidal pattern, which is the hallmark of single photon interference. The first graph was the first data taken and has more peaks and troughs visible. The second graph was taken later and shows a smoother curve, but with significantly fewer wavelengths over the same change in voltage of 60 volts. The PZT was not functioning properly, and we suspect it was deteriorating over time. The PZT had a much lower resistance than it was supposed to, which meant that the amplifier had a resistance that was too high to effectively change the voltage across the PZT. Instead, a 0 to 60 volt voltage source was used to change the applied voltage by hand. This contributes to the fact that the plotted data is not a perfect sinusoidal wave. However, even had the PZT been driven by the code, the data would not be perfectly sinusoidal. With the amount of counts measured, about 6,000 on one detector and 42,000 on the other, we would expect about 1 accidental count every 5 seconds. Also, the PZT does not change linearly with voltage. This experiment was a culmination of several quantum principles, including entanglement, superposition, and the Heisenberg uncertainty principle. The reason that interference is the expected outcome of the experiment is that the photons exhibit wave-like behavior as they travel through the branches of the interferometer. They are in a superposition of both branches as long as there is no which-way path information available. As it turns out, adding a bandpass filter in front of the detectors is essential for the experiment to show interference. Adding a 20 nanometer filter in front of the detector gives a low uncertainty in the energy of the photons. According to Heisenberg's uncertainty principle, this means that the uncertainty for the time will be higher. This minimizes the ability to gather which-way path information. A future extension of this experiment shows the effects of quantum entanglement. In this extension, which among others has been performed by Galvis, a narrower bandpass filter is added in front of the detector that detects the signal photon, which does not go through the interferometer. Simply, by adding different filters, interference is observed even when there is a greater difference in the path length. The reason for this is entanglement. Adding a narrower bandpass filter decreases the uncertainty of the energy of one photon, also decreasing the uncertainty in the energy of the other. Entanglement is what allows changing a bandpass filter in front of one detector to impact the other photon. Quantum mechanics as a whole has unlimited possibilities on how it can be used to improve efficiency in the real world. By understanding the quantum nature of silicon, we can manipulate its electronic properties and thus be able to make a variety of electronic gadgets, such as phones and laptops. In addition to that, telecommunication via fiber optics uses lasers as the light source, which are devices that use quantum principles. Furthermore, the use of smartphone navigation and atomic clocks relies on vacillations between two definite quantum states. The use of magnetic resonance imaging, or MRI, is based on the quantum nature of hydrogen atoms. Moreover, in quantum cryptography, secure information can now be transmitted as changes to the quantum states of entangled photons. Quantum computing enables a higher processing power due to the use of quantum bits over classical bits. The applications of quantum mechanics grow day by day and continue to defy our classical understanding of the world. Thank you.